So the model that we want to work on is related to capturing the process in a job shop. And let me go through the process so you will get a better sense on what we want to do and how we want to do it. So here we are trying to model a job shop in which we have an incoming queue. The jobs arrive to the incoming queue with capacity of infinity. The inter-arrival times of the jobs is 60 minutes, exponentially distributed. And then we have three machines, machine 1, machine 2, machine 3. Each one of the machines has a queue before the machine. And then these jobs, when they come to the system, they are either job A or B or C. So they come to the system as a job. The inter-arrival process is just for the jobs. But when they come to the system, we can look at them and we can say, oh, they are job A or B or C. 35% of them are job A, 40% are job B, and 25% are job C. And these jobs, depending on what type they are, go through these processes differently. For example, job A goes through machine 2 first, and then 3, and then 1. Job B goes through machine 1, and then 2, and then 3. Job C goes through machine 3, and then 1, and then 2. So this is so all of them go through the incoming, and then from the incoming, they go through these machines based on these orders specified here. And then the process time on each one of these machines is specified here. So for example, for job A, going through machine 2, the processing time is 45 minutes. And then machine 3, the processing time is 60 minutes. And then machine 1, the processing time is 75 minutes. The same for part job B and job C. Okay, and these processing times are exponentially distributed. They are random and they are exponentially distributed. So we want to model this system. The entities that come to the system are jobs, but then based on these percentages, they are either job A or B or C. They go through the processes differently. Each job goes through the process in a different order, and we have the processing time on each machine. So as you can see, even on the same machine, these jobs have different processing times. For example, job A on machine 2 has 45 minutes processing time. Job B on machine 2 has 70 minutes processing time. So these jobs not only go through the machines in the different order, but they also have different processing times on these machines. So we want to model this system and see how we can capture it. So what I want you guys is to please create a folder for week 7. And in that folder, create a new ProModel model and name the model as Job Shop. And please create these locations. So we have 7 locations. For all the queues, put capacity of infinity, first in, first come order. For all the machines, put capacity of 1. The entities that come to the system is jobs. The inter-arrival time 60 minutes exponentially distributed. And this is what we know about the process what I put in this table is what we know about the process. So I want you guys to please create the model, create the locations, create the entities, and create the arrival, and we do the processes together. Okay. So here are my locations. I have the incoming, and I have the 3 queues for machining center 1, 2, 3, and I have the 3 machining center 1, 2, 3. All the queues have capacity of infinity. The 3 machining centers have capacity of 1, and all the queues have first in, first out, or queuing order. Okay. For the entities, I have the job as my entity. And then for the arrival, I have the job coming to the system 1 at a time. The inter-arrival time is 60 minutes exponentially distributed, and these jobs will come to the system for as long as I run the simulation. Okay. For the jobs, so the entity that comes to the system is the job, and we are incoming. And now we know the probabilities that these jobs are job A, job B, or job C. So 35% job A, 40% job B, 25% job C. Can you tell me how can you potentially take care of this? That jobs are the ones that come to the system, but when they come to the system, we can look at them and with these probabilities assigned, we know they are job A, B, or C. How would you take care of this?
Are we going to assign attributes?
Okay, that's one for sure. Like what we did in the customer, in the barbershop example, we still had the customer as, we had the entities as customer, but with different probabilities, we gave them different tags or different attributes. And that works fine. The only problem is that if we are going to use the tag method to just give them a tag, then we have to just do that for, we have to check the value of the tag for every location that they go to. For when the parts go to machine 1, again, we have to look at the value of their tags. If the value of the tag is 1, for example, that means that they are and that represents part A, that means they're done with the operation and they have to exit. If the value at machine 1, if the value of the tag is 2, which represents part B, and they are at machine 1, that means now we have to send them to machine 2. And if the value of the tag is 3, representing part C, and they are at machine 1, then we have to send them to machine 2 as well. And we have to do it for machine 2 and machine 3 as well. So if all of them are in the system as jobs and the only thing they have is just their tag that differentiate between them, wherever they go, when they go to machine 1, we have to check the value of their tags to see where they have to go next. When they go to machine 2, we have to again check the value of their tags to see where they should go next. And the same we have to do for machine 3. When they get to machine 3, we have to check the value of their tags to see where they should go next. And that's perfectly fine, but that's a lot of if then else that we have to write. Okay, so we can treat this a little differently. That makes the job a little easier for us. With that, what we can do here in the destination, not only I can specify, for example, different destinations for these parts with different probabilities, but I can assign different entities. So right here, I can generate a different entity and just say that, yeah, jobs come to the system, but the entity that is going to come out is going to be job A entity with probability of 35%. And then the other entity is going to be job B entity with probability of 45% and job C with its own probability. Okay, so here I can also create different entities. Job A, job B, job C. Then I can just pick any one of these parts, job A, job B, or job C, take it to different machines, and I don't need to write any if then else statement at all. Okay, so let's try this method just for the sake of learning. Let's try implementing this method. To be able to do that, first I have to go to the entities and create those new entities that I want to name. Like if I want to create 3 and here on the destination, if I want to say the jobs coming and here I have job A or job B or job C, then let's go to the entities and create these 3 new jobs. So here we want to create 3 new entities, job A, job B, job C. Then we can go to the processing and say that, okay, the jobs are in the incoming, but the entity that is going to basically come out of incoming and go to these destinations can be job A, and job A goes to, after the incoming, job A goes to machine 2 and job B goes to machine 1. So job A goes to machine 2. So job A is the entity that is going to come out and wants to go to machine 2, but we saw in the shape of the system that they don't go to machine 2 directly. They have to go first to the queue and then to the machine. So job A then has to go to machine 2, machining center 2 queue, and that is going to happen with probability of 0.35. And the other thing is that we have job B that is going to go to machining center 1 queue with probability of 0.45 and 0.4, we have to correct that. And job C goes to machine 3 first, as you can see in the picture. Job C goes to machine 3 first with chance of 25%. So let me first correct the probability for job B. That's 0.49, not 45. And job C has to go to machine 3Q with the chance of 0.25. Okay. So we created these entities inside the system. So the jobs came in, and with these probabilities, they are either job A or job B or job C, and we can send them right away to their destinations. What would be the other option for the destination here, guys? Do you remember when we learned how to assign the attributes in the move logic? Remember, we tried two things.
Sorry, could you repeat that?
So what is the other way for me? What is the other approach for me to write the destination? Right now, the parts come into incoming, and right there, I send them to destinations right away. I tell them, okay, what type of entity they are, and I send them to the destinations right away with these probabilities. What would be the other method to do this? Not the other method, what would be the other possible thing that I can put in the destination?
Incoming queue.
Exactly. I can keep them at incoming and assign these and define them as job A or B or C, and then send them to from there I can send them to their own destinations. Okay, that would be possible. Okay. Now for job A, as we can see here, job A goes to machine 231. Okay. So for me, the easiest way to do this part would be the click method. So I'm going to pick job A here. Job A. Job A, let me just check one more time. 231. Okay. Job A already is at machining center 2Q. From the queue, we go to the machining center 2. And then from machining center 2, we go to machining center 3Q. And then from the machining center 3Q, we go to machining center 3. And then from machining center 3, we go to machining center 1Q. And from the 1Q, we go to machining center 1. And from there, we go to exit. Right? 231. Okay, I just did the click method. It's just because it's a lot faster. And here we also see processing times on these machines. 46, 60, 75 exponentially distributed. $45, $60, $75. Okay.
Because we need to put weight
Yeah.
in front of each one of them.
Yeah. Thank you. Okay. Job B goes to machine 1, 2, 3. So I'm going to pick job B. And we're already at incoming queue. And from there, we go to machine 1 queue, machine 1 queue to machine 1, machine 1 to machine 2 queue, machine 2 to machine 2 queue to machine 2, machine 2 to machine 3 queue, and machine 3 queue to machine 3. And then from machine 3 to exit. Process dump 70, 70, 50.
Wait, sorry, why do you show job B at incoming?
Give me 1 second. What did you say?
Right there, when you have job B right there in incoming, why do we, isn't it already at the machine 1 queue?
Oh, yes. Job A is already at machine 1 queue. We go to machining center 1, and then machining center 1 to 2 queue. Okay. And then for job 3, we're already at machining center 3 queue. So from there, we go to machine 3, 1, 2. To machine 1 queue. $50, $60, $60. Okay. Okay, so we have when the part jobs come to the system, we have job A, B, C with these probabilities, and we send them to the destinations right away. And then each one of the jobs goes through its own process, takes their processing times, and then finally they leave the system. And I want you to tell me, because when I run this model, okay, let's run this first for 80 hours. Now we see it since, so basically the jobs come in and they are transferred into job A, B, C. Now we have total exit for job A, B, C separately. And what I wanted to ask you guys was that if I want to calculate the total jobs, total job A, total job B, total job C that have left the system, all we need to do is to create three random variables and just increase them when job A leaves the system, and when job B leaves the system, and when job C leaves the system. If I want to calculate the total exit for job A and B and C. That's something that the simulation has already calculated for you. That's why I'm not insisting that we have to that we do it in this model. But if we wanted to do that, like you have done this many times so far, if I wanted to calculate the total exit for job A and B and C in the model ourselves, all we have to do is to create 3 variables for job A, for job B and job C, and just increase them when we are done with those jobs and they are about to exit the system.